Okay, hi. So I want to look at this idea of adding binary numbers and to build a circuit. But we want to be able to build a circuit that's going to take into consideration the carry. Okay, so let's just think about this for a minute. Okay, so first of all, to think about it, we need to look at the binary addition rules. Okay, so and the binary addition rules say, well, we have 1 plus a 0, which is going to be a 1. A 0 plus a 1 is going to be equal to a 1. A 0 plus a 0 will be equal to a 0. And a 1 plus a 1 is going to be equal to a 0. And then we're going to carry the 1. So we saw in a previous video that we can construct what's called a half adder, right? And the half adder takes in two binary digits and produces a value for the sum and the carry. Okay, and let's just consider this again a little bit, right? So if I was to rewrite the binary addition rules and say that, well, if we have, or we take a look at where we have 1 plus a 1 being equal to a 0 and a carry a 1, or then we have 1 or a 0, or 1 plus a 0 is equal to a 1. Well, here we're really carrying a 0, and we have a 0 plus a 1 is going to be equal to a 1, and again we're going to carry the 0, or a 0 plus a 0 is equal to a 0 carry a 0. And this is what we want to construct, okay? So we want to have some kind of logic gate that, giving these kind of inputs, produces this output, and a gate to produce this output. So we can map these ones and zeros down to trues and falses. So we have an input A and an input B, and it's true, true, false, false, and B is true, false, true, and false. Well, this is the same configuration, right? Because we have 1 and 1, 0 and 0, 1 and 1 being true, and 0 and 0 being false. So the output of this gate here, this is what's known as the exclusive OR gate, and this looks like a traditional AND gate. Okay, so the XOR gate will say that this will yield a true only when we have an odd number of trues going in as the input. Okay, for the XOR gate and the AND gate, both inputs have to be true for it to actually yield a true or yield a positive 1. So now when we draw this circuit, the circuit should look something like this, where we would have inputs A and B, and then we pass. So we know that the XOR gate, this is going to give us the sum, right? So this gets us the result, or the sum, and then the AND gate we need as well is going to give us the value of the carry. So if we take an A and a B and we pass this into an XOR gate, we get out the sum. And now if we take an input here from A and an input from B, and we pass these into an AND gate down here, well, this gives us the value of a carry. And as we can see, the output of these gates up here, so when A is 1, and let's consider this for a second. Well, if we have the value right? Or the Boolean or the binary addition of 1 plus, sorry, let me rub that out, of 1 plus 1 is equal to 0, and then we carry a 1. Well, if I was to pass in a 1 here into a 1 into B, well, the output of the XOR gate, so 1 XOR 1 is going to yield a 0. And then if I'm passing a 1 down here, so I'm just taking the input from this particular gate, 1s are going to travel down here, so 1 and 1 is going to actually output a 1. So I can see for this particular setup here, well, when A is 1, A is equal to 1 and B is equal to 1, well then S is going to be equal to 0 and C is going to be equal to a 1. Okay, I can see the output of that particular construction. Great. So the issue I have though, right, is with this is what's actually known as a half adder now, right? So we take two binary bits and we simply join those bits in and we're able to produce out a sum and a carry, right? But the issue is with a full adder, we also need to account for the carry. Okay, so now let me just clean this up a tiny bit. I'm going to rub out just this particular example here. Okay, we won't be finished with the carry quite yet. We get rid of this, this, and this as well. Okay, so we also need some kind of carry in, right? So we're going to call this a C in, right? And when the carry comes in, we need to do something with that carry, okay? So what we're going to do is we get the resultant here from the XOR gate, and I'm going to pass in the carry to it. So if we were to consider this in a particular, I suppose, simple addition, well, what it would actually look like is that we would have this option of where we have a 1 plus a 1, and then we have the value of the carry, yeah, like that. So this can be 1 or a 0 in our addition. So a 1 plus a 1 is going to yield a 0, but if we have a carry of a 1, well, if the carry is 1, it's going to be a 1, and then it's going to carry a 1. Okay, so it's going to look like this. Okay, so what we need to be able to do is to think about the output of this initial gate. We're going to pass this into an XOR gate, which is going to produce similar enough to how we produce the half adder. It's going to produce the sum, taking into consideration the carry that's coming in. Okay, so what we're going to do first off and foremost is we're going to take in the carry in, and we're going to pass this in to an XOR gate with the resultant of the original sum from, I'm going to say that's our new sum, coming out from the half adder. Okay, just like that, XOR, yeah. And now what we need to be able to do is, well, we need to take, just like we would have done in the half adder, we need to take the input down here and pass this in to an AND gate with the carry coming in. So we're going to AND those two together, and this will produce the carry, or the carry in a half adder. And so then either when this AND gate up here, we'll just highlight this, so when this AND gate is true, or when this AND gate is true, well, the resultant carry out should be equal to a 1. So let's just finish this. So we're going to, and this. So what we're going to do is we're going to pass this gate and this gate into a resultant OR gate, like so, and then this is going to produce the carry out. Okay, so now we've built our full adder, and what we can do here is we can see, and we're going to test it now. So for example, the very simple test that we'll do is we'll say, as a quick test, we'll say if we want to add 1 plus a 1 with a carry of 1. Okay, so now let's annotate these. Okay, so what I'm going to do is I'm going to have a little look here. So we're going to do this along the wire tracings. So we have a 1 coming in here, a 1 coming in here, and a 1 coming in on the carry out. So the 1 and a 1 goes in. What we're expecting to find, by the way, is what we need to find is actually that we get a 1 and a carry of a 1. So the new sum will be equal to a 1 and the carry out is going to be equal to a 1. So this is what we're hoping to get. Okay, so let's follow these tracings a little bit. So if we have a 1 and a 1 going into the XOR gate, well, exclusive OR tells us only one of those has to be true. So we're going to now pass the resultant will be a 0. Then the 1 and the 1 go into the AND gate down here. And 1 and 1 is going to yield a 1. Okay, now let's follow this 1 up here. So now going into this particular XOR gate here, we're going to have a 0 and a 1. And a 0 XOR 1 is going to yield a 1, which is the resultant of this XOR gate up here. And now what happens is we're going to pass the 0 down and the 1 into this particular AND gate, which will yield a 0. So now the final OR gate, we have a 0 going in or a 1, and this will yield a 1. So the resultant of our full adder circuit here is able to add 2 binary numbers and take into consideration a carry coming in and have a carry going out. Okay, so that should make sense. And really the important thing is that we get to look at our binary addition and how this maps down into the other gates. So we have the XOR gate and we have the AND gate. And we can start to construct this circuit. Okay, I hope that makes sense. If it does, we'll draw a little happy face and hopefully it's quite clear. Okay, thank you.